In this section, we're going to do an example buffer problem and 2 additional exercises. So if a buffer solution is created by dissolving 0.3 moles of sodium cyanide in 510 milliliters of 0.55 molar HCN, and the Ka of HCN is given, we're going to find the pH of the buffer, and then find the pH after 0.10 moles of sodium hydroxide is added to the solution. So in part A, we're just finding the solution of the buffer, so that's what's in the flask. All that we have in the flask is 0.55 molar HCN, which is a weak acid. Okay, so we don't even need we need the salt and the weak acid, but we don't need any information about sodium hydroxide. So let's look at how we solve it. We have a weak acid buffer, and there are 2 reactions going on. One reaction is the weak acid equilibrium. The other one is the salt reaction that goes to completion. The weak acid is 0.55 molar, and the sodium cyanide is 0.30 moles divided by the volume to get 0.59 molar. And remember, if NaCN is 0.59 molar, then so are the sodium ion and the cyanide ion. So we can solve this either using an ice chart. If I use an ice chart, the initial concentration for my HCN would be 0.59. So if I were to do an ice chart, I would put 0.59 here, and then how they change according to X, and at equilibrium, and you could solve for K, or solve for X using the K expression. However, since we do have an initial concentration for CN, which is 0.59, we can go ahead and use Henderson-Hasselbalch. Remember, Henderson-Hasselbalch is pH equal to pKa plus the log of the basic ion, or the basic species, over the acidic species, which would be 0.59 over 0.55 in this case. When you do that in your calculator, you should get 9.24. So the pH of this buffer solution is 9.24. We're going to move on to part B, because part B requires 2 steps, of a before and after chart, and then either Henderson-Hasselbalch or a ice chart. Here's what's in the beaker. In the burette, I have a strong base, sodium hydroxide, and I'm adding 0.10 moles of sodium hydroxide to the solution, which is really not really in a burette. We're just using that concept of titration to do this. But if I add 0.10 moles of something, you know that that's not a volume, so it's not how much volume of sodium hydroxide I'm adding. But I'm adding 0.10 moles of sodium hydroxide to this weak acid buffer. So the first question you ask yourself is, which ion do I need to control? So since this is a buffer solution, I'm adding hydroxide ions, so somehow I need to consume these hydroxide ions so that they can be converted into something else so that my pH stays the same, or relatively the same, okay? So then you ask yourself, which ion or what species in the beaker will it react with? Is it going to react with the acid, weak acid, or its conjugate base? Well, if HCN is OH minus as a base, it's not going to react with another negative ion. So most likely it's going to react with the HCN. So the OH minus reacts with HCN. All right, HCN is an acid. It's going to donate that proton and make water. So that's why we end up with water and the cyanide ion. And by doing this, we're converting the OH minus into conjugate base, which is pretty weak, so our pH can remain relatively the same. Okay, so the first step is to do a before and after chart, because we have to consume those hydroxide ions first. So here's the reaction we had on the last slide. Remember, in the before and after chart, we can only include moles. We cannot include molarity. So if we have a molarity, we have to multiply by the volume of that species in order to get the number of moles. So I had 0.10 moles of hydroxide because that's how much I was going to add. HCN, to get that, is 0.55 times 0.51 in your calculator. That would be 0.28. Over here with cyanide, I made a mistake on the slide. So this is not 0.9, it's 0.59 because that was the concentration of cyanide ions. 0.59 times 0.51, and that is still 0.3. So this is still correct. And remember, we don't need water. So since I have less hydroxide ions, it's going to be consumed, and I'll add that to the cyanide ion side. So after this reaction, after the hydroxide is consumed, there's 0.18 moles of HCN left and 0.40 moles of CN minus left. You divide that by the total volume of the solution, and these are the concentrations of HCN and CN minus. That's your first step. Your second step is to either do an equilibrium reaction, equilibrium reaction in an ice chart, or I can put these two numbers into my Henderson-Hasselbalch equation. On this side, I show you both. If I were to do an ice chart, this is what the ice chart would look like. If you were to use Henderson-Hasselbalch, it would look like this. But you can see that either way you do this, you still get 9.56 for your final pH. So no matter which way you decide to do it, either one should work. However, whichever way you choose, just make sure you completely, fully understand how to do it that way. Okay? So then when we compare, before we added NaOH, the pH was 9.24. After it's 9.56. So the buffer effectively maintained the pH. The pH did not go out of control when we added the hydroxide ions. Let's try this example with adding solid NaOH to a solution from sample exercise 15.2. From exercise 15.2, we had 0.5 molar acetic acid and 0.5 molar sodium acetate in the buffer solution. First, you need to decide what the hydroxide ions are going to react with so that your pH isn't changing. It's two options, either the acetic acid or its conjugate base, acetate ion. Since hydroxide is negatively charged, it's not likely to react with the acetate ion, so it's most likely going to react with the acetic acid. So now we write the reaction of the hydroxide ion with the acetic acid. And we're going to do a before and after chart. Remember, before and after charts can only include moles. So in this case, there's 0.10 moles of OH minus because that's how much I'm adding. The moles of acetic acid is 0.5. I had a 0.50 molar solution, but there's 1 liter, so 0.5 times 1 is 0.5 moles. And the same process for acetate ion. 0.5 times 1 liter is 0.50 moles. And I think I have this backwards. I think it's not 0.10, it's 0.01 up here. So it's 0.01 moles of hydroxide ion. So that's the one that's going to be consumed. And then after the reaction, the hydroxide's gone. There is 0.49 moles of acetic acid left and 0.51 moles of the acetate ion. Divide that by the total volume, which is 1 liter. Moles over liters equals molarity. So this one's 0.49 molarity, and this one's 0.51. The second step is to use these concentrations either in an ice chart or Henderson-Hasselbalch. So I'm going to use Henderson-Hasselbalch for this, and the Henderson-Hasselbalch in this case is pH equals the pKa, which is 4.74, plus the log of the basic species, which is the acetate ion, and the concentration of that was 0.51, over the acidic species, which is the acetic acid, and that was 0.49. If you do that in your calculator, you should get that the pH is equal to 4.76. Now let's compare this to a solution of water. If I were in water and I'm adding sodium hydroxide to 1 liter of water, sodium hydroxide is a strong base, so I just look at the concentration of the hydroxide ion. So the concentration of the hydroxide ion would be 0.01 moles divided by 1 liter. So the molarity would be 0.01 m. Using that number, I can find the pOH. If I take the negative log of 0.01, I get 2.00. And then the pH would be 14 minus 2.00, which is 12.00. So you can see that if I have sodium hydroxide and water, that makes a very basic solution, okay, versus this pH, which is still acidic, even though I added sodium hydroxide to it. In this example, we are calculating the pH of a solution. That results when we add 0.1 moles of HCl to 1 liter of the buffer in sample exercise 15.5. If you look at sample exercise 15.5, that was a 0.25 molar solution of ammonia, which is NH3, and then 0.40 molar solution of ammonium chloride, NH4Cl. So these are the two species that I have in the beaker, a weak base and its salt. So first you have to ask yourself, I'm adding HCl, and the hydrogen ions is what's possibly going to change my pH by lowering the pH. So what are the hydrogen ions going to react with so that my pH is maintained? I have two options, either the ammonia, which is the weak base, or the ammonium chloride, which is the salt. So it's either going to react with the ammonia or the ammonium in this case. All right, so either ammonia or ammonium. Since the hydrogen ions are positively charged, it's not going to react with the positive ammonium ion, but it will react with the ammonia, that's the weak base. So let's write that reaction. So this is what the reaction looks like, and then I need to do a before and after chart with moles. The moles of HCl that I'm adding is 0.10. The moles of ammonia is 0.25 times 1 liter. 0.25 times 1 is 0.25. Ammonium ion is 0.4 times 1, which is still 0.4. So I'm going to consume the hydrogen ions over here and add 0.1 moles of ammonium over there. So afterwards, I have no hydrogen ions left, which is good because my pH won't change by much. And then I have 0.15 moles of NH3 left and 0.50 moles of ammonium ion left. If I divide by the total volume, which is 1 liter, then the concentration of this is 0.15 molar, and this one is also 0.15 molar. Oh, sorry, 0.50 molar. So your next step is to use Henderson-Hasselbalch. In this case, I could use pH equals pKa plus log of basic over acidic, but since I have ammonia, a base, I'm going to be using the pKb, not the pKa, all right? So instead of using this equation, I'm going to use the pOH equation because makes the problem a little bit easier. So if I take the negative log of the Kb for ammonia, it's 4.74. And don't think that the pKa is always going to be 4.74. For ammonia and acetic acid, those are two unique ones because they're the same. The Ka for acetic acid is the same as the Kb for ammonia. Plus log of since I'm using pOH, I want the acidic species on top, which is the ammonium ion, 0.50. And then the basic species is on the bottom, 0.15. If you do that in your calculator, the pOH will be equal to, you get 5.26. You subtract from 14, and you get the pH is equal to 8.73. If you compare that to the pH that was in exercise 15.5, that solution had a pH of 9.05. So it went from 9.05 to 8.73. So it did go down because we added the hydrogen ions, but not down significantly enough to change the pH too much. So this was a good buffer solution.